All right, so let's get started. So on example 1, it says use the graph to answer the following questions. So then we have state the value of f of 2, estimate the value of f of negative 2, for what values of f of x equal to 2, estimate the value of x such that f of x equals 0, find the domain and the range, and find the intervals of increasing and decreasing. So to find f of 2, we have that our input value is going to be 2. So we go to the x value is equal to 2, and we find where the input x is on the graph, which is going to be right here. So that ordered pair would be 2, 2, so the value of f of 2 would be 2. We do something similar with f of negative 2, so exactly the same thing. We go to negative 2. And this time it asks us to estimate, and so we would see that our ordered pair is negative 2, and if we estimate using the eyeball metric, I would get 2.75. So we'll say that's approximately 2.75. And then for what values is f of x equal to 2? In this case, we have f of x is equal to 2. So f of x is a y value. So we're going to do the same thing, but this time we do it where y is equal to 2. And we want to find all of our points where the y value is equal to 2. So that's not there. Here, and we've already got this one here. So we can see that the first one is when x equals 2, and then down here, once again, we need to estimate. So I would say x is about negative 2.25. We can do a similar thing for finding when f of x is equal to 0. And f of x equals 0 is the x-axis, or that is the same as when y equals 0. It's the same as the x-intercepts. And we see that this graph has exactly one x-intercept, and that happens when x is about negative 2.75. So then finally, for a continuous function, the domain and the range are going to be from the smallest x to the largest x. So our domain is going to be from negative 4 to 5, and our range is going to be our smallest y to our largest y, which is going to be negative 3 to 3 in this case. And finally, where we're increasing and decreasing, our graph is increasing when it goes up, so that's going to be from here to here. And our graph is decreasing when it goes down, which is going to be from here to here. So for our increasing, we're going to go from negative 4 to negative 1, and our decreasing is going to go from negative 1 to 5. So graphically is just another way to represent a function. It just represents a whole bunch of input-output pairs, and that gives us our input-outputs for that question. All right, so example number 2 is using the algebraic or representation of a function where we associate our input-outputs with numeric or variable values. So our first one wants us to find f of negative 3. And that means everywhere I see an x, I will replace it with negative 3. Negative 3 squared is 9. Negative 4 times negative 3 is 12. Plus 2 gives us 9 plus 12 is 21 plus 2 is 23. What you may not know is that we can also use our graphing device to help us evaluate this function. So if we bring our calculator over here, we have x squared, so we press our y equals, we put in x squared minus 4x plus 2. And then if we quit back to our home screen, we can press alpha and trace, and it gives us the ability to select y1. And if I just do parenthesis -3, it will evaluate that function that I saved into y1 at x equals -3. And notice we got the output 23, which corresponds to the value that we got doing it manually. All right, part B says we want to evaluate f of -x. Well, this is telling us everywhere we see an x in f, we are going to replace it with a -x. So we are going to have -x squared minus 4 times -x plus 2. So -x times -x gives us positive x squared. -4x times -x gives us 4x plus 2. So then f of -x in this instance would be x squared plus 4x plus 2. All right. Doing something similar, f of y plus 1 would ask us to replace all of our x's with y plus 1. So we would have y plus 1 squared minus 4 times y plus 1 plus 2. And if we so desired, we could expand that out and simplify. So the square of a binomial, y squared plus 1, is going to be y squared plus 2y plus 1. Distributing our -4 into our parentheses, we get -4y minus 4 plus 2. So then finally, collecting all of our like terms, we get y squared minus 2y, and then 1 minus 4 plus 2 gives us -1. We can do the same thing with more than one variable. So if we go f of x plus h, we would then have x plus h squared minus 4 times x plus h plus 2. And we could once again multiply all that out and simplify, but that is also a perfectly good answer depending on what we're trying to do. All right, so let's take a look at our next example. So example number 3. We're asked to use f of x to answer the following questions. And the questions are to evaluate and then eventually graph this thing. So if we want to find f of -3, that's telling us we want to input -3 in for x. But since we have a piecewise function, we have to determine which domain that fits into. And we'll notice it fits into the top domain because -3 is less than or equal to -2. So that means we're going to use the top rule, which is x plus 4. So we're going to get -3 plus 4 gives us 1 for our output. And back in the previous example, we saw how to use the calculator to calculate f of -3. Well, it turns out we can do the same thing with a piecewise function, but the way we enter a piecewise function into our calculator requires a little bit more work, and then we can do exactly the same thing. So if we hit our y equals button, we get our calculator, and we get our graphing interface. So when we're going to be putting this in, we have to put our rule in parentheses and the corresponding domain in parentheses. So I go parenthesis x plus 4, close my parentheses, and then I'm going to open another set of parentheses to put in the domain. So I go x, and to get the less than or equal to, I'm going to need to go into my test menu. We'll notice test is the secondary function on the math key. So you go second and test, and then I'll notice my less than or equal is choice number 6, is less than or equal to -2. I hit -2, close my parentheses, and I'm going to press graph to show what this does. So now my calculator draws this, and notice when it gets to -2, the graph stops, because we're only graphing x plus 4 on the domain. X is less than or equal to -2. So let's go back in and put the rest of them in. So to continue doing this, we go on that same line, and we go all the way to the end. And we're going to separate each of the parts with a plus function. So we go plus, and then we're going to do the same thing, parenthesis 2, and then another parenthesis for our domain. To put in a compound domain, we need to rewrite as the two different parts. So we're going to have -2 is less than x, and then the second part is x is less than or equal to -4. So now back on our graphing calculator, we're going to go -2, second math to get our test menu, is less than x, close our parentheses, then another parenthesis, x, second math to get our test menu again, is less than or equal to 4. Close our parentheses. So then this time when we press graph, now we get the first part, and there's the second part of our graph, and notice it ends at x equals 4 where it's supposed to. So we go back in again, y equals we get to the end of all of our stuff, and we go plus, and we put our last rule in, which is -x plus 6, close our parentheses, open our new set of parentheses, and we put in x is less than or equal to, oh, sorry, not less than or equal to, x is greater than 4. And now when we press graph, we're going to see we get the whole thing. The cool thing about putting this into your calculator as such, now if we need to evaluate things again, so we were asked to find f of -3, and our calculator gives us 1, which is the same thing. So then we go alpha trace y1, and we go f of 1, and that's going to give us 2. Our next one wants 5, so alpha trace of 5, and we get the value of 1 again. And it's also worth noting that you can get it in the traditional way by going to the table and just scrolling around. So if I go down to 1, I'll notice my value is 2, and if I go to 5, I see my value is 1, and then if I scroll up to -2, my value is still 2. So we can use our graphing device to get some nice outputs for a piecewise function, and then when we have the graph, we just press our graph key, and we also get a very nice graph. You can do all of these by hand, and I know in Math 187 you probably did it both ways, by hand and on a graphing calculator, but as functions get more complicated, it's going to be easier to create good piecewise graphs with your graphing calculator than going through all the legwork to do it by hand. All right, so the next examples, in fact all the ones on this page, are going to be involving some function shifts. So we want to describe how the graph g of x equals 1/2 times x minus 3 squared plus 4 can be obtained from the graph f of x equals x squared. So in our notes in Canvas, we have some basic functions and what they look like on one of our handouts. So we have something that looks like this, and then more importantly, we have some very nice shifting rules to remind us how these things shift our function around. So in our first example, we have g of x is equal to 1/2 times x minus 3 squared plus 4. And each of these things do something different. So the x minus 3 is going to shift the graph right 3 units. We then have our 1/2, and it's going to shift the graph shrink the graph by a factor of 1/2. And then the last thing that's going to happen is the plus 4, and that's going to shift the graph up 4 units. So it's going to take our parent function for a parabola, move the parabola 3 units to the right, shrink all the y values by a factor of 1/2, and then move all of the y values up 4 units. So we do the same analysis with our next function. So once again, we have following function. We have g of x is equal to 3 times the absolute value of x plus 5 take away 1. And so we can do our same analysis. We have our 3, we have our x plus 5, and we have our minus 1. So we're pretty much going to have the same thing happening in the sense that now we have an x plus 5, so this is going to shift the graph left 5 units. The 3 is going to stretch the graph by a factor of 3, and the minus 1 is going to shift the graph down one unit. So I was getting all of these things from this table. So if we add a number after a function, it shifts it up. If we subtract a number after a function, it shifts it down. If we compose, so it's on the inside with a function, if we add, it shifts it left. If we compose it with x minus b, it's going to shift the graph right. A number on the outside, c or d, either stretches or shrinks the function, and it depends on whether or not the absolute value of the number in front is bigger than 1 or less than 1. If the absolute value of the number on the outside is bigger than 1, it's going to stretch the graph. If the number is negative, it would also reflect it across the x-axis. If the number multiplied by on the outside is less than 1 in absolute value, it's going to shrink the graph, and if it were a negative number, it would also reflect over the x-axis. The last two are as if the composition is on the inside, it also does some stretching and shrinking. So back to our example, we notice that in G, we had the number on the outside was 1/2, so it shrunk the graph. In the second example, the number on the outside was 3, so it stretch the graph. As mentioned, we had composition. We had replaced x with x minus 3. So minus 3 shifted our graph to the right. Here, we had replaced x with x plus 5, so it shifted it to the left. The number on the outside, if it's positive, shifts the graph up, and if it's negative, it shifts the graph down. So this is the reoccurring theme for all of these problems. And as we saw, this handout just has a nice summary of all of these things. So let's take a look at our next two. And see what we end up with. All right, so example 6 says, describe how the graph of g of x equals 1 over 10 times x plus 5 can be obtained from the graph of f of x equals 1 over x. So we have a couple of different ways that we can think about this. So we'll notice that this first part right here, the 1 over 10x can actually be realized in two different ways. If I were to evaluate f at 10x, that would mean everywhere I see an x in 1 over x, I replace x with 10x. That would give me this part. But I could also realize this as going 1 over 10 times f of x, because 1 over 10 times f of x would be 1 over 10 times 1 over x, which would give me 1 over 10x. So notice that there are two different ways that we can get that expression. But if we parse out the language on that other sheet, they will both give us the same correct answer. So the reason I mention this is that if you're working with someone or a tutor, there is going to be more than one way to do this problem. And as long as you end up with the same solution in the end, the path that you use to get from A to B is irrelevant, as there's more than one way to get there. So then, for either of these, if we look at our handout now, we'll see if we do the 1 over 10 times our function. Well, 1 over 10 is less than 1, so that would put us here. It's going to shrink the graph by a factor of d. So it shrinks the graph by a factor of 1/10. If we look at the other one where we're doing the composition of 10 times x like we have here, so then it's going to, it says stretch the graph by a factor of 1 over d, but 1 over d is 1 over 10, which is the same thing that we got the other way. So either way that we resolve this, we are going to get the same answer in the end. So the first thing that happens is we're going to, 1, shrink the graph by a factor of 1 over 10. And then the next part, plus 5, is going to shift the graph up 5 units. All right, so we look at our next one, and we want to know how we're going to get the graph g of x equals 1 over x plus 5 can be obtained from the graph of f of x equals 1 over x. Well, this one we want to recognize as function composition, because we are going to replace x with x plus 5. So we'll notice that f of x plus 5 would indeed be 1 over x plus 5. So that's composition. So then that's going to shift left 5 units. So now in our next two examples, we're given graphs instead of functions, and we're asked to do the same shifting. So if we look at each of these, here I have a -2 and I have a +3. So the -2, so the part in red, is going to reflect across the x-axis because it's negative and stretch by a factor of 2. So the first thing that's going to happen is we're going to flip our graph over the x-axis and stretch by a factor of 2. So we'll notice this branch of the graph is at -2. If I flip it over, it's at +2, and then I double it, it's going to start by looking like this. Then this branch right here is at +3, so if I flip it over, it's going to go to -3, and then I double it, so it's going to be at -6. And we just connect these two things here. So that's our first part. And then the next part, the +3, is going to shift up 3 units. So then I take all of my y values and I move them up 1, 2, 3. So my graph is going to look something like this. I go up 1, 2, 3. And I get something that looks like this. Now analyze example 9. The first thing I have is my x minus 6. So that's going to shift right 6 units. And then I have a +7. And that's going to shift up 7 units. So if I do each of these, I'm going to shift right 6 units. So I go 1, 2, 3, 4, 5, 6. And then I'm going to shift up 7 units. So 1, 2, 3, 4, 5, 6, 7. So my first bit's going to do this. And then I'm going to shift this guy right 6 and up 7, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So I get this, and then something that would look like that. So I would just take my graph, and it's literally like I pick it up, I move it to the right 6, and then I move it up 7 to get my new picture. For example 10, we're asked to find the exponential function f of x equals c times b raised to the x that contains the point f of 1 equals 24 and the point f of 3 equals 864. Well, each of these represent an ordered pair, so this is the ordered pair 1, 24, and this is the ordered pair 3, 864. If we plug these into our model or our function here, we have our first one says if I input 1, I should get out 24. So that gives me the equation 24 equals c times b raised to the first power, or in other words, 24 equals c times b. If we plug in our second ordered pair, we get 864 is equal to c times b to the third power. This gives us a system of equations in c and b. So if I solve the first equation for c by dividing both sides by b, I get c is 24 divided by b, and then I can substitute that into the other equation, and that gives me 864 is equal to 24 over b times b cubed. So then one of our b's reduces here, giving us a b squared, and we get 864 equals 24 b squared. So then we would divide both sides by 24, divide by 24. So 864 divided by 24 gives us 36. So 36 is equal to b squared. So then taking our square root, we get b is equal to plus or minus 6. And we'll reject the negative solution because we need our base for an exponential to be positive. So we get b is 6. And if b is 6, then c is 24 divided by 6, which is 4. So then our model is going to be f of x is equal to 4 times 6 raised to the x. So we can also do this on our graphing calculator. So this is just an example of a regression. So if we press stats on our calculator, when we go to edit, we can put in our two ordered pairs. So our inputs are 1 and 3. The corresponding outputs are 24 and 864. So then to do the regression on our calculator, we press stat, we go over to calculate, and we scroll down until we find, in this case, we want an exponential regression, so EXP regression. And we just go through our list, and it'll think for a second, and it gives us the following output for our exponential regression. And we get y is equal to a times b to the x, where a is 4 and b is 6. So that would be y equals 4 times 6 to the x, which is the exact same answer that we got. So we can use the regression function on our calculator to help us do regressions of functions as well. All right, our next one reads as follows. So suppose you are offered a job that lasts 1 month. Which of the following methods of payment provides the most money? Find the amount. $1 million at the end of the month, or on the first day, 2 cents, on the second day, 4 cents, and on the third day, wow, I really messed that up. 8 cents. Assume that a month has 30 days. So the first thing we're going to notice is that we're going to have a geometric sequence. So AN, our first day is going to be 2 cents. So we're going to go 0.02, 0.04, 0.08, and that pattern continues forever. So our formula for a geometric sequence is AN is equal to A1 times R to the n minus 1. So our A1 is easy, it's just the first thing in the list, and we find our common ratio R by doing any term divided by the one that came before it. So 0.04 divided by 0.02 gives us 0.0 or gives us not 0.02, it gives us exactly the number 2. So that's going to be our R value. So we put that in, and that gives us AN is equal to 0.02 times 2 raised to the n minus 1. And now we want to sum this up for the first 30 days. So we may remember the formula for S sub n for a geometric series is A1 times 1 minus R to the n all over, so A1 times 1 minus R to the n all over 1 minus R. So in our case, that would be 0.02 times 1 minus R, which is 2 to the 30, all over 1 minus 2. And if we type that into our calculator, we go alpha y equals to get our fraction. We get 0.02 times 1 minus 2 to the 30th power, all over 1 minus 2. We press enter, and we get this value. It's also worth noting that we can just do this in sigma notation on our calculator. To do sigma notation, we go alpha, window, we grab our sigma as choice number 2, and our sum is going to start at 1, and we have 30 days, so go from 1 to 30, and then we put in our geometric sequence. And if we press enter, either way, we notice we end up with the same solution, whether we sum it up using our formula for a geometric series or just the sigma notation. So now, if we look at this value, put in some commas to help us read it, we notice that if you started with 2 cents the first day, 4 cents the second day, 8 cents the third day, at the end of 30 days you would get $21 million as opposed to $1 million. So the second option is definitely going to be better for this. All right, so now we're on to some inverses. So we want to find the inverse of a function. So there's really 4 steps for finding the inverse of a function. So the first thing we do is we replace f of x with y. And that gives us y equals 3x minus 1 all over 8x plus 5. Step 2 is we interchange x and y. So that's going to give us x equals 3y take away 1 all over 8y plus 5. And then step 3 is we solve for y. So in this case, our y is in both the numerator and denominator of a fraction, so that makes it a rational function in y. To solve a rational function, you clear the fractions by multiplying both sides by the LCD, and in this case, our LCD is 8y plus 5. So then on the right side, our denominators reduce out, as they always should, when you multiply by the LCD, and then we distribute. So we distribute our x into our parentheses, so we get 8xy plus 5x, and then on the right side we get 3y minus 1. So now we need to get all of our y's on one side and all of our x's on the other. So I'm going to minus 8xy and minus 8xy. I'm going to add 1, I'm going to add 1. So then these reduce out and those reduce out. So we're left with 5x plus 1 is equal to 3y minus 8xy. So now I need to finish solving for y by factoring out my common factor of y. So that leaves 3 minus 8x times y. And then on this side I have a 5x plus 1. So then I divide by 3 minus 8x, and I divide by 3 minus 8x. And finally, that leaves me with y equals 5x plus 1 all over 3 minus 8x. And lastly, step 4 is we replace y with f inverse of x. So we would get f inverse of x is equal to 5x plus 1 all over 3 minus 8x. And if you wanted to, you could clean that up by factoring out some minus signs, and your answer may have looked slightly different if you would have got all your y's on the left side instead of the right side. But regardless of which way you did it, you'll end up with an equivalent algebraic answer. So pretty much the rest of the problems in this section are going to go down the same way. So the first thing we're going to do is replace f of x with y. So y equals 1/3 times 4 minus the natural logarithm of x. So then step 2, we interchange our x and our y. So x is equal to 1/3 times 4 minus the natural log of y. And now we need to solve for y. In this case, our y is trapped inside a logarithm, so this is a logarithmic equation. So we need to isolate our logarithm. So to solve, the first thing we need to do is multiply both sides of the equation by 3. So we get 3 times x is equal to 3 times 1/3 times 4 minus the ln of y. So the 3 and the 1/3 reduce out, and we're left with 3x equals 4 minus the natural log of y. So we minus 4, we minus 4, and that gives us 3x take away 4 is equal to the negative natural log of y. Divide by minus 1, and divide by minus 1, and that gives us negative 3x plus 4 equals the natural log of y. So then finally, raising both sides of the equation to the e in order to reduce out our natural logarithm, because e and natural log are inverses, we finally get y is equal to e to the negative 3x plus 4. So then our inverse f inverse of x is e to the negative 3x plus 4. Alright, so the next two build on that idea, but instead of functions this time we have just some equations. So we wish to solve the following equation. As we just saw in the last example, the inverse, or the opposite of an exponential, is a logarithm, and the inverse of a logarithm is an exponential. So if we take the logarithm of both sides of this equation, the e and the natural log will reduce out, and we're left with just 3x take away 4 is equal to the natural log of 2. After doing that, this is now a linear equation, and we can just solve for x by adding 4 to both sides. We get 3x is equal to 4 plus the natural logarithm of 2. Divide by 3, and we get x is equal to 4 plus the natural logarithm of 2 all over 3. Similarly, we do the same thing that we did in the previous one. We're going to raise both sides to the e. So both sides become an exponent on the base of e. And then the e and the natural logarithm reduce out. And that leaves us with 7x plus 1 is equal to e cubed. And now it's linear in x, so we isolate x by subtracting 1. And that gives us 7x equals e cubed take away 1. Divide by 7, and we get x equals e cubed minus 1 all over 7. And those are our two solutions to each of those problems. All right. Coming up on the last page, we have the following. And for these ones, we're going to need our unit circle. So we need to find the exact value of each expression. So if we take a look at our unit circle, which will be helpful. Our first problem wants us to know, or wants us to find, when is inverse tangent equal to -1? Well, by definition, tangent is y divided by x. So if y divided by x needs to be -1, that means y and x have to be the same number but have opposite signs. So we need y divided by x to equal -1. Well, that happens in exactly two places on our unit circle. Here, y and x are the same but have opposite sign, and here, y and x are the same but have opposite sign. So the tangent inverse is equal to -1 at the angle 3 pi over 4 and down here at 7 pi over 4. And in fact, we could keep going around the unit circle, so we're adding, it looks like a pi when we go in each direction. So that would be -pi over 4, and this would be 11 pi over 4, and so forth. And the way that we can write that is we pick either of these solutions, and we would write something like 3 pi over 4 plus pi times n, where n is in z, for every integer. So the sine inverse of 1/2 is going to be the same thing, but sine, by definition on the unit circle, is y. So we need y to equal 1/2. So where does y equal 1/2 on our unit circle? Well, we have a 1/2 here, and we also have y equaling 1/2 here. And then in quadrants 3 and 4, y is negative, so it can't be down there. So we get our first solution is going to be pi over 6, but then we could also wrap around the unit circle, so plus 2 pi n. Our other solution is going to be 5 pi over 6 plus 2 pi n for each trip around the unit circle. And that would be our inverse values for each of these and the exact values for those. So then our next one wants us to simplify the following expression. So we have the tangent of the cosine inverse of x over 2. So the key idea here is we need to recall that inverse trig functions are angles. So then that means this is the ratio of the side of a right triangle. So I'm going to call this theta. And if I were to just draw a generic right triangle, cosine by definition is adjacent over hypotenuse. So my adjacent side is x and my hypotenuse has to be 2. I can solve for the missing side using the Pythagorean theorem. So by the Pythagorean theorem, we'll call this side y. We have x squared plus y squared equals 2 squared, and we want to solve for y. So we minus x squared, we minus x squared, we get y squared equals 4 minus x squared. Taking our square root, we get y is equal to the square root of 4 minus x squared. So now we're asked to find the tangent of that angle. Well, by definition, the tangent of theta, tangent is opposite over hypotenuse. So it's going to be y over x. So we get that the tangent of theta is equal to the square root of 4 minus x squared over x. So we were able to simplify that to the algebraic expression square root of 4 minus x squared over 4. And that would be its simplification. All right. Well, this is our last question from the review. Does the sine of the sine inverse of 7 pi over 4 equal 7 pi over 4? Explain. So we might think that since they're inverses, that these two things just cancel out, and then we would get 7 pi over 4 all over, or just 7 pi over 4, because those two things reduce out. So what we have to remember is that the sine inverse has a restriction on its domain and range. So when we made the inverse of the sine function, we inverted the sine function, but only on the interval from negative pi over 2 to positive pi over 2. And so then that became its range, and its domain was the range of the original sine function, which was negative 1 to 1. And if we ask our calculator ever so nicely, well, what is the sine inverse, sine inverse of 7 pi over 4, we get a domain error. So since the inner function is not in the domain, we cannot then take the sign of an error. So we need to be careful. With trig functions, with inverse trig functions, we have restricted domains. The domain of sine inverse and cosine inverse is -1 to 1. So 7 pi over 4 is not in the domain.